All right, my apologies for the delay. We are ready to go. Let me just find my pen here. Whoa, my pen is huge. There we go. All right, so let's remember where we are. We've introduced the concept of an antiderivative. We have renamed that to the indefinite integral. So let's remember, because it's going to be important to distinguish between these concepts. The indefinite integral has the integral sign like that, then my function, then, oops, a little ugly, but the dx to reference my variable in question, and to have the second purpose of the substitution method of being a separable differential. So this represents represents a new function, a new, well, really, a family of functions, a family of functions, and that such that these functions have as derivative this f of x, whose derivative is the function in question. So it's in as close as it can be the reverse of the derivative concept. In the derivative concept, I was given a function. I use my properties to get a new function. That new function corresponds to the original in some way, but it's a new function. Here, I also make a new function, and its connection to the original is that its derivative is that original function. Okay. So it's very important to remember that what I'm getting is another function, really a family, but you can just put that to the side as a technicality right now. Okay. Now let's look at something seemingly very different. Let's look at area. Now, what is fairly reasonable to want to have a tool for is it's always nice to, if you look at surveying land and things like that, to have a nice straight line for your area. And then you can use basic geometric formulas to calculate the area. But what if I have a border that's a little bit more curvy? Then it might be beneficial to use functions to describe this line before I can calculate the area of the enclosed space. When they're not straight lines, functions aren't far behind to describe those curvy lines. Now, to make it as easy as possible as a first step for us, we're going to we're going to set it up with just one curvy line. And say here is our XY coordinate system. Let's suppose we have a graph like that. That is whoops, going to correspond or come from some function. And let's suppose we're interested to enclose the space between two x values. Let's say this one is at x equal to a, and the other one is at x equal to b. So now I'm interested in this blue area. So this blue area is not, it's close to a rectangle, but it's not exactly a rectangle. And it's very important to accurately calculate what this area is. So in the simplest case, I have straight lines. I can just put it on the x-axis, and I'm asking for the area. We casually say the area under the graph y equals f of x on a to b, from a to b, but really it is, to be more accurate, between the graph of the function and the x-axis, to be more precise. But for our initial step, it's always going to be our straight line boundaries between two x values and the x-axis. So we casually say the area under the graph, but it stops at the x-axis. So there's usually no confusion there in this first basic case. So now the question is, what on earth is this area and how is it related to the function? That is the question. Now to do that, we have to explore this blue area a little bit to understand why it's connected to this function in the way that it is. So what are we going to do? Well, to start, I'm going to make a function that is based on this area. And I'm going to just duplicate this so we have a clear starting point. So let me just go back to black here. X-axis, Y-axis. So it doesn't really matter. Let's make it up and down. There's my function. It's graph. Doesn't matter what it looks like. And I'm going to go from A and ultimately I do want to go all the way to B. Oopsie. That is my goal, to get this whole area. But I'm going to say, I don't know how to do that. So instead, let's just go part of the way. And I'm going to stop at a random x value. And I'm going to calculate not the whole area, but just try and figure out how I can work with the area from A to X. So we're not going to make that blue. Let's make that maybe a very, very light blue, because it's not our complete area. So we're just going to try and figure out how I can work with the area from A to some X value. So let's go back here. So let's define a function. Define an area function. Let's call it A for area. And then I need to have the input X, because I need to know where to stop. And it's going to be the area under my graph from A to some x value. Now a is always fixed. A is fixed. The x is the variable. If you want to pick a small value of x just bigger than a, I'm going to get a really thin area, really thin slice here. And as I increase this input where we want to stop with our areas, our light blue area is going to get bigger. So ultimately, we have a little bit more wiggle room with our area by changing the right endpoint uh, of this light blue area. It's a little bit more flexible. But ultimately, we want to know what is the area from A to B. So let's write that here. We want to know the area from A to B, and that is then going to be our big A function, our area function, with little b as the input. So ultimately, I'm making this function so that I have something to explore, but ultimately, I'm only interested in plugging in the b once I've figured out what this function is. But I can't do that until I know more about this function. So our question now is, um, what what is the function, this area function? If I can figure out what this area function is and what it's sort of behind the scenes, I just gave it a name, right? I want to peek behind this name to understand what it looks like. So when I plug in the B, I can actually get some sort of answer. In order to do that, I need to figure out what this function, this area function is. Well, first, two things I can certainly note, and that is that if I plug in little a, sorry, I'm just going to mute you because there's background noise that keeps popping up. Let me know if you want to ask a question. If I plug in little a, then my left boundary and my right boundary sit right on top of each other, and I get no area whatsoever. So separator line there. And like we've said, if I plug in B, that is the area that we want. The area we want. Now let's name this. Let's just call it area we want. Let's break a line here from A to B. That's going to be our name. We can name it whatever we want. It's the area we want. Okay. So let's make a new page here. And let's figure out how can we make sense of this area. I'm just going to redraw this to not jump back and forth. So that one sketch doesn't get too cluttered. I'm just going to copy this, whatever the area may be, coming from my function, or whatever the line may be coming from my function. I have my A. My left boundary is always fixed. And I'm going to go to some x value. And we colored that light blue. It's not quite what we're looking for because I have to move x over to where I want it to be eventually. but that's good. Okay, so what I'm going to do now is switch to black, is go a little bit further. Not a whole bunch, just a little bit. Now I'm going to exaggerate it here, but it's really a very tiny step forward from X. So I'm going to take a little step forward and I'm going to make that step size H. Then I'm not sitting at X anymore, but I'm sitting at X plus H. Now in truth, that's a really, really small step, but so that we have room to draw stuff, I'm going to exaggerate it a little bit. Okay. Now, if we want to find the area from, let's write it out, area from little a, not to x, but to x plus h. We can approximate that, or let's say not can, let's say is. We can approximate that by saying it's this blue area. Let's go blue, the area from a to x plus this little slice. Let's zoom into this little slice. Now, even though the top of this little bar looks straight, it's not. It's part of this bendy, curvy function. But I can approximate that with a rectangle. Let's zoom in some more. I can approximate that with a rectangle by making the top horizontal and nice and straight. Then this rectangle, let's color it purple. This rectangle, if the little gap that I moved forward, h, if h is small enough, then the error that I'm making is pretty small. It's pretty small. So this is now a rectangle, which is easier to work with. Its area is the height of the rectangle times the width. Well, the width is h. The height of the rectangle, it sits at x. It's a point right there on the graph. How do I find the height? It's the y value, so it's f of x. So let's zoom out. So I don't know exactly what the area from little a to x plus h is, but I know it's the light blue area plus my approximation by way of the rectangle, which is h times f of x. So this is then approximately the actual area from a to x plus h, but that has a name. That its name is area function with x plus h, the right boundary as the input. So I have this approximation, which isn't a bad approximation, because if my little extra purple gap that I step forward is really small, this error that I'm making is going to be very, very small and actually gets smaller as h gets smaller. Let's just rearrange this approximation equation. I have h times f of x is approximately a of x plus h minus a of x. And then I can divide both sides by h to get the function value approximately this expression on the right. Now, let's write this down. This approximation gets more and more accurate, accurate as h gets smaller. And in fact, we're doing a very casual approach to this. It's not mathematically formal and precise, but in truth, what you get is that as you look at the behavior of this, a of x plus h minus a of x over h, as h gets closer and closer to 0, it stabilizes to the function value. Now, what does this remind you of? This is the limit definition of the derivative of the function in question, in this case, a. So what does that mean? That means that my area function has f of x as the derivative. So the area function a is an antiderivative of f of x. I'm going to put a box around that. Antiderivative of f of x. So when I go back to this page over here and remember what we were ultimately asking, we wanted to know how the area from A to B, or any area under the graph, is related to the function that the graph comes from. And now we can see that that area function is related to the original function by being its antiderivative. The area function is an antiderivative of the original function, f of x. So we're pretty much done here. So here is the punchline. The area that we want, let's write it out, from, not, yes, from will come, but first, the area under the graph of the function, I have to say between which endpoints. From A to B, this is the area we want. First of all, let's notice that because A of B is what I want, and big A of little a, the left endpoint, is 0, I can say it's the area function at B minus the area function at A. Now this is important because I don't necessarily, without getting into too much technicalities, I don't necessarily know which antiderivative I'm working with. So if I want to take any antiderivative, because there's a family of them, I have to do this subtraction, where my A function is any antiderivative of the f of x function. Without getting into too much technicalities, feel free to ask me if you're not sure. But we're just trying to get to how are we going to calculate this area. So if I can find, I'm not going to do this whole limit definition setup, getting to why, what the link is. Now that I have the link, I'm just going to use that. So in order for me to find the area under the graph between two x values, I have to find an antiderivative and I have to plug in the right x value and plug in the left x value and subtract the two. Now it would be nice to give this a name, just so I don't write out area under f of x from a to b every single time. And because this area is so closely linked to the antiderivative, I want to have a name that is similar to the name of an antiderivative, the indefinite integral. But it's not the same, right? Before, we noticed that my indefinite integral represents the whole family of antiderivative functions. Now I'm going to take one of them, any one of them, and plug in x values and get a calculation. This area is going to be a number. So I can't use exactly the same naming system, but I do want to remind myself, I do want the name to remind myself that I'm working with antiderivatives here. So all we're going to do is we're going to change this a little bit by putting the left and right boundary values with the integral sign. And this is how we're going to find it. And we're going to call this the definite integral of my function on some interval a to b. So by specifying the x values, I now need to know, oh, now I am looking at an area specifically. I still calculate that area by way of antiderivatives and a little calculation, but it's not exactly the same thing, though they are coming from a similar place. Okay, so here, whoopsie, here is what we need to know. Now let's make a new page and look at some problems. Let's just start with the first one. We are looking for the area between the function in question and the x-axis on the given interval. Let's just do the first one, 2x minus 14. What was that, 12.6? 12.6. First one. So the area is, what was my function? 2x minus 14. 2x minus 14, x is my variable, and the x values are 6 to 10. Now, we can do this in two ways because I have a very, very simple function to start with. Let's visualize that. This function is a straight line, and if I graph y equals 2x minus 14, my y-intercept is going to be at negative 14. My x-intercept is going to be what? Well, I can do a little scribble here. If I plug in 0, let's say I'm looking for the y-intercept, sorry, x-intercept rather, plug in 0 for y, 2x minus 14, so x is going to equal 7. So if I'm interested at That is a horrible, horrible example. Let's change this. I don't want this to be my first example. Let me just fix this real quickly and not look at a specific problem, as I don't want that for my very first one. I just randomly picked the first one, but it's a little bit much. It's a little bit too much right now. So we're just going to make that an example, and let's just make this an 8. Okay, so my x-intercept is 7. I'm coming through the x-axis. There's my line. That's my line. 8 is going to sit over here, let's say, and 10 over there. There we go. 8 to 10. And I'm interested in this area. Good. Now, because this is a basic geometric shape, a trapezoid, I can calculate this area and confirm what we get. But for the cases where, this is just a good first example, for the cases where this is more curvy, this top boundary, I can't do simple geometric formulas anymore. I have to I have to unfortunately rely on my calculus. So I leave it to you to confirm that my answer that I get with the calculus root is in fact correct. Now let's see what this new fancier calculus area calculation tells me to do. So first, I need to find an antiderivative. So an antiderivative, let's put a little arrow there, antiderivative of 2x minus 14. Well, that's going to be x squared minus 14x. Now, I can't leave my answer like this because the area answer is a number. So this represents a number. Yet my antiderivative is a function. Those two things are not always equal. So I'm just going to say here, look, I know this is temporary. I'm going to put a line here to mention that I still need to plug in my x values. I'm not done. This is just one of the two steps. I need to find an antiderivative first and then plug in the numbers. So then I plug in the 10 to get 10 squared minus 14 times 10 minus plug in the bottom number, 8 squared minus 14 times 8. Always plug in the top minus plug in the bottom. So let's ask our math bot what we get, but you should do that with me just to be sure. And we get a nice and convenient 8. And I can, of course, calculate that by the area of the trapezoid as well. A half times the height between the parallel lines times the sum of the parallel lines. We could, let's just scribble it over here. Check with our trapezoid area formula. this. So I have half, not h, sorry, force of habit. The gap between them, is that the right formula? Let's suppose. I'm gonna leave it to you. Since I'm running out of time, I see I'm just a little distracted. Check with the trapezoid area formula that you get the right answer. Just so we can run through more and more questions. We only have 6 minutes left, I see. So now we're gonna, whoa, what just happened? Stop it. Whoa, what is happening? Looking for there are my area questions. Oh, there we go, okay. So before we worry about the area more, I just want to make sure we are okay with the difference between an indefinite integral and a definite integral. There's a very slight difference in that when I have a definite integral, I still have to find the antiderivative and everything. I just have to go a little bit further, just a little bit, by plugging in the values top minus bottom. So if I take, for example, something simple, give me something simple. Let's say this one. Number 6. Let's make a new page here. Before we actually put the area layer on top, let's just practice the definite integral. What was it? 0.5 to 1. Uh, X cubed minus e to the 4x. Now that's not a straight line anymore, so I really have to use my calculus to find the area, whatever that might look like. So the definite integral, when I see numbers on my integral sign, is find the antiderivative, like always, x to the 4, 1 over 4, minus e to the 4x, and that's going to need a 1 over 4 correction as well. I'm not going to care about the plus c, because I'm just looking for an antiderivative. And then I'm going to plug in the number. So that is the part that's different. If you write a plus c there, when I plug it in and minus the next one, the c's will just cancel anyway, so it doesn't matter. So now I have to plug this in. So again, I'll write it out to emphasize what we are doing. But of course, because it's a 1, it is certainly a little bit easier than usual. Plug in the top boundary value minus the answer I get when I plug in the bottom boundary value. Now the 0.5 is a little less convenient, but still, that is how we're going to do it. So you don't have to write this out, but I'm doing it just to emphasize what is the calculation step doing. Plug in the top minus plug in the bottom. That is not going to change. So let's calculate that. Not quite sure how to do E in MathBot. Let me just check this. Is it just E? Okay, okay, That's good. Let's now do the calculation. Please check that I get the same calculation. And now we're going to get, according to this, negative 11.57, let's say. Now, I don't care right now what the answer is. Negative, positive, small, big, I don't care. We're going to do, we're going to have to figure out exactly what these answers mean and clarify some things. Right now, I want to get used to what a definite integral is, uh, what it is, and how it's different from the indefinite integral. It's the same start in that I'm finding an antiderivative, but I go one step further, plug in the top number, plug in the bottom number, and get whatever answer I get. Then, once we're comfortable with that, we have to look at, okay, what can these different answers actually mean graphically? So for now, feel free to practice just the definite integral, 12.5. Don't pay attention to any answer that you get, but we're going to just do a couple more of these before we move on to the area tomorrow, just so we can see how bad does it get and what do I need to watch out for. Then we'll put the area layer on top. All right, that is where we will pause things today.